In this video, we will be working on Euclidean geometry for grade 11. So this is our first practice problem. But before you attempt any practice, it is important to understand the 10 theorems and how to apply them. Here we have 7.2. It says in the figure, O is the center of the circle ABCDE. DB is equal to DF. AODF, BOE, and BCF are straight lines. Angle CFD is 10 degrees. It's really important and actually essential that you read the given info. There'll always be important information given at the top, and sometimes not all of the information is indicated on the diagram. In this case, it is where we see that angle CDF 10 degrees that is on our diagram. We also notice that they mentioned that DB and DF are equal. So those two strokes indicate equal sides. Now it says calculate, giving reasons, the size of the following angles. And remember, in Euclidean geometry, whether you're in grade 10, 11, or 12, every time you make use of a theorem, a rule, even something from Fun X where you have parallel lines, you need to write down a reason based on the rule that you used. So 7.2.1, we need to calculate D2. We notice that it is 3 marks. So the mark allocation helps you to understand the amount of work that you need to do in order to get that angle. Since it is 3 marks, we are most likely going to need 2 steps, so we probably need to calculate another angle first and then use that to get D2. Now firstly, analyzing our diagram and seeing where D2 is located. Here is D2 on the diagram. Now it's important to ask yourself, which 2 points subtend to D2? So you guys will notice that points A and B subtend to D2. But if we follow A and B, the only other angle that it subtends to would be O1 at the center. However, we don't know what O1 is. And AB also subtends to angle F, but that does not help us. So that is not based on any grade 11 theorem at the moment. However, what we do notice is that we have got this triangle, which I'm going to call DBF. And in this triangle DBF, we notice that BD and DF are equal in length. That makes this triangle an isosceles triangle. So what we actually know here is that if this triangle is an isosceles triangle, then it would mean that these 2 corners are equal to each other. Where angle F is 10 degrees, angle B3 would also be 10 degrees. Okay? But remember again, you are no longer allowed to say isosceles triangle. Instead, we use our reason as equal angles opposite equal sides. So let's write that down first. So 7.1.1, that was angle B3, which is 10 degrees. And our reason is equal angles opposite equal sides. This reason can be further abbreviated if you choose to write down an equal to sign instead of the word equal. Okay, so how does this help us? Now that we know what angle B3 is, we realize that D2 is actually an exterior angle of that triangle. If we take this line DF and we extend it, what we notice is that this creates angle D2 that lies outside the triangle. So if we have a look at this separately, this is what it looks like. And it's a lot easier to notice it in this diagram. Here D2 is the exterior angle of the triangle, and we know that, as a rule, the exterior angle of a triangle is equal to the sum of the interior opposite angles. So here, angle D2 is going to equal to angle B3 plus angle F. But since you are in grade 11, there is no need for you to write down the broken down format of it where you show which two angles you are adding to get D2. Instead, you can just give your answer. Working with this, since it is equal to angle B3 plus angle F, angle D2 would be 20 degrees. So here, angle D2 is 20 degrees. So we can write that as part of our answer. Angle D2 is 20 degrees, and our reason is exterior angle of a triangle. So this makes sense as to why it was 3 marks. Okay, let's move on. The next angle we need is angle A. So let's first locate angle A. So here is angle A on our diagram. And what we notice is that angle A is subtended by points B and D. So B and D subtend to angle A. So that's what that looks like. They subtend to angle A. And B and D also subtend to angle E, which means that angle A and angle E are equal to each other. Had we known what angle E is, then we would just be able to use angles in the same segment. However, we don't know what angle E is, so we need to find another way of getting angle A. So, looking at the diagram, what we realize is that angle A is also part of this triangle, which I'm going to call triangle ABD. And I need you guys to notice that in triangle ABD, we already have one corner of that triangle. We've got angle D2 as 20 degrees. If we can get the other corner, which is made up of B1 and B2, then we can just use sum of interior angles of a triangle to get angle A. Now this can be quite easily done if you remember one important theorem from grade 11 called angles in a semicircle. So you guys need to realize something here. This line AD is a diameter. And we know diameter goes from one end of the circumference through the center and to the other end. So where you've got this diameter, it subtends an angle of 90 degrees on the circumference. And that is always the case. The angle subtended by a diameter on the circumference of the circle is 90 degrees. So we can start off by getting B1 and B2, but let's give it a proper name. We can call it angle ABD. So we're going to say angle ABD is 90 degrees. That is angle in a semicircle. And now that we have ABD, we can easily calculate angle A. So all we have to say is 180 minus 90 minus 20, and we get angle A. So if we just calculate that, because remember, you just need to give your angle and the reason, so you don't actually have to show the calculation, but 180 minus 90 minus 20 leaves us with 70 degrees. And we used the sum of the interior angles of a triangle. Another reason that you could use is just interior angles of a triangle. Sometimes angles of a triangle is accepted as well. Okay, so now let's fill that in on our diagram. And it's quite important that whenever you calculate an angle, you always fill in its value on your diagram, because you will always need it to calculate further angles. Now, moving on to 7.2.3, we need to get angle O2. So here is what you're going to notice about angle O2. Angle O2 is at the center. So here we have it at the center. Angle O2 is subtended by point B and point D. So notice B and D subtend angle O2 at the center. B and D also subtend angle A at the circumference. So BD subtends O2 at the center, BD also subtends angle A at the circumference, and what do we know about this? We have a theorem that matches to this. This theorem says the angle at the center is 2 times the angle at the circumference, which means that O2 is going to be 2 times 70, which makes angle O2 140 degrees. Now this makes sense because this question was 2 marks, so 1 mark for the angle, 1 mark for the reason. So from here onwards, the remainder questions are also for 2 marks, so they should be quite straightforward. The next angle we need is angle C1. Okay, so let's locate angle C1 on our diagram. Here it is. And just by having a quick look at this, you should realize that angle C1 is part of a cyclic quadrilateral. So the cyclic quadrilateral that I'm focusing on is this, which I'll refer to as ABCD. So how we know that it's a cyclic quadrilateral? Firstly, it is a 4-sided shape. All 4 corners lie on the circumference of the circle. That makes it a cyclic quad. Now, in a cyclic quad, we know that the opposite angles are supplementary. So if we take angle C1 and we add 70, we should get 180 degrees. That means that angle C1 is 180 minus 70, which is going to be 110 degrees. So that was quite simple. We can write this answer as angle C1 is equal to 110, and our reason is opposite angles of a cyclic quad, which we just write as CQ. Next, we are looking for angle E. So let's refer to our diagram and locate angle E. Okay, so here is angle E, and I had actually mentioned something really important to you before, where I said that points B and D subtend to angle A, points B and D subtend to angle E as well. So if you have 2 points on the circumference and they subtend to more than one angle that lies on the circumference, those angles are equal in length, meaning that angle A and angle E would be equal in size, okay? They'll be equal in size because of angles in the same segment. So angle E is 70 degrees. Okay, let's write that down. Next, we are looking for angle C2. So let's refer to our diagram. Here we have angle C2, and there's 2 ways of doing this. An easy, basic way, without even using anything from grade 11, would be to just use angles on a straight line. You guys know that angles in a straight line are supplementary. They add up to 180 degrees. So we can just say 180 minus 110, and angle C2 would be 70 degrees. So another way of doing this, which would use grade 11 Euclidean, is to identify this cyclic quad. And notice that C2 is the exterior angle of the cyclic quad. And remember how the theorem goes. The exterior angle of the cyclic quad is equal to the interior opposite angle. So here you see that angle C2 would equal to angle A, which is 70 degrees. So sometimes when it comes to calculating angles, there are more than one way of doing so. Not all of them may require you to use a grade 11 theorem, but as long as what you are doing is valid and it is a rule from geometry, it will be marked correct. So for this, I'm just going to stick to the grade 11 theorem, exterior angle of a cyclic quad. that was angle C2, 70 degrees exterior angle of a cyclic quad. So the last angle that we need to calculate is angle O3. Let's locate angle O3. So here we have angle O3. And here's something that stands out, and something important for me to mention to you guys. They absolutely love testing isosceles triangles in grade 11. But the way in which they test them is that if it's not explicitly stated that this is an isosceles triangle, and if they want to trick you a bit, what they usually do is they hide the isosceles triangle inside the circle, where here we have an isosceles triangle called OBD. Okay, let's redo that. Okay, here's triangle OBD. And what I need you guys to notice, what makes this an isosceles triangle is that OB and OD are equal to each other. So you may ask, okay, but why are they equal? You guys notice that OB is a radius. OD is also a radius. Since OB and OD are radii, they are equal in length, making triangle OBD an isosceles triangle. Since it is an isosceles triangle, we have two sides equal and two angles equal, meaning that here, angle B2 would equal to angle D2, so angle B2 would also be 20 degrees. But why is this important? Why do we need angle B2 to get angle O3? You guys notice that O3 is the exterior angle of that triangle. Okay, notice the line BO being extended, it creates O3. If O3 is the exterior angle of the triangle, angle O3 would be 20 degrees plus another 20 degrees, making angle O3 40 degrees. But that's not the only way to do this, okay? I'm just showing you this because I needed to show you the isosceles triangle part of it, but I want to show you another way of getting this. So before I do that, let's just write down this version of the answer because there may be some of you that would have done it this way. So remember, we calculated B2 first and then angle O3. And since we are no longer allowed to say isosceles triangle, instead we say equal angles, opposite equal sides. And then we can say that angle O3 is 40 degrees. That was the exterior angle of a triangle. Now, let's look at the other way of getting the same answer. So this now uses something from grade 11. I want you guys to notice that we've got points E and D on the circumference. They subtend to angle O3, which is at the center. They also subtend to angle B2, which is at the circumference. Okay, I'm going to repeat that. Points D and E subtend to angle O3 at the center. Points D and E also subtend to angle B2 at the circumference. And what we know is that the angle at the center is 2 times the angle at the circumference. So that is the grade 11 way of getting this answer, which actually would still require you to get B2 first, since we didn't have that initially. So if you are going to use this is how you would write down your answer. You'd still start off by saying angle B2 is 20 degrees and have the same reason as before. Okay, equal angles, opposite equal sides. But to show what angle O3 is, when you mention 40 degrees, you would say angle at center. So remember, angle at center is 2 times angle at circumference. So grade 11s, please remember that in order for you to excel at this section, at this topic, you guys need to do as much practice as you can. Every question is different. Every question's application is different. Even though we have the same theorems, in some diagrams, it's a little more difficult to identify those theorems that need to be used. Also remember that from your paper 2, majority of the marks come from Euclidean geometry. So it's crucial that you do as much practice as you can if you want to excel in mathematics. Okay, make sure to check out the rest of the videos where I cover further practice on Euclidean geometry. Please remember to like, subscribe, and turn on your notifications for more content.